All right, maximum likelihood estimators. What even are they? We're going to figure it out. But before we do that, we're going to start with an example. All right, say your friend told you that he'd ran a Poisson simulation and he'd observed those data points, 4, 4, 6, 3, and 4, and he wanted you to guess what parameter he'd used. All right, say lambda. And you're like, well, I can't read your mind. How am I supposed to guess? So what you decide to do is, all right, let's say lambda equals 2. All right, the probability of observing those data points is that. All right, and then you say, all right, I'm going to do that for all the values that it's probably going to be. It's obviously not going to be 1,000,000, or at least it would be very unlikely. So you're like, all right, I'll do the ones I'll calculate the values of lambda that are the most likely. Honestly, it's probably going to be 4 or 5, but I just did 2 to 6 to show you the kind of general shape, and I've sketched it on the right. And that's kind of that is what we're doing with maximum likelihood estimators, is we're trying to maximize the value of P. And the way that I calculated those values is I said, let's say lambda is 2, the probability that I observe 4 times probability that I observe another 4 times probability that I observe a 6, and I times them together since they're independent. And that's going to become really useful when we look at the likelihood function, so we know what we're doing when we do that. So I would say to my friend, lambda is probably 4. And that makes sense. If you have lambda is unlikely, it's unlikely to be 6. It's unlikely to be 2. You probably guess that, but those are the calculations, all right? It's intuitive. We're just looking for the value that maximizes P. All right, and obviously for Poisson distribution, it's a discrete distribution, so it's not continuous. So it's a little bit icky, but that's the essence of what we're doing, is with all the complicated calculations and differentiation that we have to do and taking logs, this is what we're doing, is we're saying, all right, let's just find the value that maximizes P. That is the maximum likelihood estimator. Okay, so now we're going to look at the likelihood function, which looks confusing, but it's not, all right? Think about what we just looked at, okay? So all this is saying is to calculate the likelihood function, we take the product, that's what that little pi means, we take the product from I equals 1 to n, so that means however many values we've observed. We take the product of these values, the probability that we observe that value. So for example, say lambda's 3, probability that we observe a 4 times the probability that we observe a 5 times whatever probabilities we've observed, right? That overall will calculate the probability that we observe that whole set of values, okay? That's the likelihood function. And again, we're trying to maximize that value like we just saw. So all this is doing is saying for a general random variable, because it's not always going to be Poisson, right? Theta just represents the parameter. It could be lambda in this case, it could be mu, it could be n or p, it could be anything, right? This is just for a general case, okay? And it's the same with continuous random variables. All we've done is we've shown the probability density function, right? That's f of x instead of p of x, okay? So it looks complicated, this px and fx, but all it's saying is that that's the function, and it depends on the value of theta that we're fixing, right? In our case, it was lambda, it could be 3 or 4 or 5. We're fixing that, and the function also depends on the value of xi, all right, or what we've observed, basically. That's all that means. So it looks scary, but just think about what we just did, okay? We did the probability that we observe that set of values, and we have to maximize that, okay? That's all we're doing. Okay, and sometimes we talk about the log likelihood function, okay? And this just means, obviously, as the name suggests, we're just taking the log of the likelihood function. And the only reason we do this is because it makes life a lot easier. usually. When we're working with exponentials and we need to differentiate, taking the log makes things a lot easier. And we're allowed to do this because the log function is increasing and it's 1-to-1. So it's pretty well behaved. So any value that will maximize the likelihood function will also maximize the log likelihood function. Okay, and I've drawn a really quick, rough sketch to demonstrate that. It's very rough, so don't get mad at me. But say the likelihood function looks like something on the left, the log likelihood function will look like something on the right. Okay, we don't really care about the shape of the graph. All we want to know is the value of x that maximizes it. And that is the same for both. Okay, so now we're going to look at the likelihood function of a Poisson distribution. Okay, so I've written at the top there, the likelihood function for this is a function of lambda and x, and it's the product from I equals 1 to n of 1 over xi factorial times lambda to the xi times e to the minus lambda. Okay, and what we're going to do is we are going to take the log of that because it's going to make things a lot easier when we need to differentiate. So it looks really nasty, all right, taking the log of this. But, right, simplify things. I've highlighted or underlined that little bit there and called it A. Okay, so you know that when you do log ABC, it equals log A plus log B plus log C. So instead of having 3 terms though, like we do in the red, we've got n lots of them, right? But we're doing the same thing. Instead of taking the product, right, when we take the log, it's gonna give us the sum, okay? So the sum of log and then A plus log B plus log C, but this time we've got the sum of log 1 over xi factorial lambda to the xi e to the minus lambda. Okay, and to help us understand how to split it up further from here, okay, from this line to this line, I've written some extra help for us here, okay? So let's say we have log a1, b1, c1 plus log a2, b2, c2 plus log a3, b3, c3, okay? That's what we've got up here. We've got n lots of that though. We're summing up the log of a product of things, okay? What we do is we're going to group together the A's, we're going to group together the B's. I ran out of room, but we'd group together the C's. Okay, that's all we've done, okay? So we're splitting it up, okay? Here we split up log A1 plus log B2, log A1 plus log B1 plus log C1. We're going to do the same here. And then we're going to do that n times. And then we're grouping them up, A, B, C, okay? Sorry, I just rubbed that out. Whoops. It's green now. So we've grouped together the xi factorials, okay? But we've got a negative sign because it's 1 over xi factorial, okay? So we take the negative to the front because it's an exponent, okay? It's xi factorial to the minus 1. So because of log rules, we take the minus 1 to the front. So we've got negative the sum of all the logs, okay? Log xi factorial, okay? Like we've got here. We've got the sum of the log of a's, okay? Next, we do the same thing, but this time with the lambda to the xi, okay? And so we split it up. We've got the sum of the log lambda to the xi's, all right? But since every time we're adding the log, we have a power to the xi, we're going to take the xi to the front, and so we're adding together log lambda, and the coefficient is just going to be the sum of the xi's, okay? Like if you were adding up log lambda squared plus log lambda cubed plus log lambda to the 4, you take the exponent to the front, you're going to get 2 log lambda plus 3 log lambda plus 4 log lambda and so on, okay? So that's why the coefficient is the sum of the xi's times log lambda, okay? And finally, we do the same thing for C. We group together the e to the minus lambda. And we're doing the same thing, but log e is just 1, okay? I should clarify that we're working in base e. That's why we've taken the log, because we've made things easier. So log e is 1. And again, we take the minus lambda to the front. We're going to get minus n lambda, okay? We're doing the same thing, all right, we're doing exactly the same thing with lambda, but since e is a constant and log e is 1, we know that we're going to get n minus n lambda, okay? Okay, so now we're going to differentiate the log likelihood function, okay? So again, it looks complicated, but we'll think it through. So this term here is a constant with respect to lambda. Okay, we're differentiating with respect to lambda. There's no lambdas here, so this is going to equal 0 when we differentiate it, okay? Here, ignore the sum first. Ignore the sum, sorry. Ignore this part. Say we just had log lambda. We know when we differentiate that, we're going to get 1 over lambda. And since this is the coefficient, we're simply going to multiply 1 over lambda times this, okay? So that's how we have this term. We've just put it into 1. The sum of the xi's times 1 over lambda. That's all we've got. Just like if you want to differentiate 5x, it goes to 5. Because if you differentiate x, you get 1. You can times it by 5. You can think of it like that. We're doing the same thing here. And here, differentiate n lambda, you're going to get n. Okay, just like 5x goes to 5, n lambda goes to n. Okay, and strictly speaking, what we need to do here to prove that we are going to maximize the value, we need to take the second derivative and show that it's less than 0. Okay, you'll remember that when the second derivative is negative, we're showing that we have a maximum. Okay, so we've taken the second derivative, and again, it's a little bit complicated, but just think about it, right? We have this over lambda. So we can rewrite this as, hold on, this can go to the sum of the xi's times lambda to the minus 1. Sorry, this is really unneat, okay? Just think of it like that, okay? And again, if you were to differentiate that, it's going to be negative sum of the xi's lambda to the minus 2, okay? So that's what we've got here. We've got negative, because you can think of it as lambda to the minus 1. You times it by minus 1, take down the power minus 2. That's how we've got this guy here, okay? So we see that this is going to be negative, so we've shown that we're going to be maximizing with this value, okay? Okay, so we've shown that this value that we've calculated here will maximize the log likelihood function when it equals 0. Okay, that's just a fact of calculus. When you set the differential, you know, when you set it equal to 0, okay, it's going to maximize the function. You know that. And so here we've got this up here equals 0, and then you rearrange, you're going to get lambda equals the sum of the values over n. Okay, obviously you add n to both sides, multiply by lambda, and then divide through by n. That's how you've got here. And so that's pretty intuitive. All we've done here is we've shown that to maximize our value, we're going to sum up the data points and then divide by n. But we kind of already knew that, you know, that's kind of what your intuition is. If you're given like a bunch of data points, 4, 5, 7, 10, 2, 8, and you're asked to estimate the parameter, you're likely going to be thinking, all right, I'll add them up and divide them by the number that I have, the number of data points. But we've shown that that's why this is going to give you a good estimate, okay, because it's going to maximize your likelihood function, okay? And so often in exams, they'll ask you to go through this whole process with maybe a binomial distribution, maybe a normal distribution or an exponential, but every time the process is the same. You write the likelihood function. If there's exponentials, you'll probably want to take logs. You differentiate, you take the second derivative to show that you're maximizing. Okay, there's other steps you can do as well, but that's normally what I would recommend. It's normally the easiest, but it's not the only way. And then you set it equal to 0 and rearrange for your value of your parameter, okay? Okay, I hope this has been helpful. If you do have any questions, then leave a comment and I will be happy to answer and help you out as soon as I can.